some stochiometry calculations and problems so that you can understand how to first determine the mole ratio. So, the purpose of this tutorial is to go over some stochiometry calculations and problems so that you can understand how to first determine the mole ratio when given a chemical equation, as well as how to convert from mole to mole, and then from mole to mass, or in grams, or from mass to mass. Because there are several questions that you can answer from one given equation. So that's what we're going to do. I'm going to do some examples of chemical reactions, how you would set it up, and how you would do the various calculations. So what I've started off with here is a skeleton equation of nitrogen gas plus hydrogen gas, which yields ammonia. So we see, if we look at this, then we'll notice that this is an unbalanced equation. And before you can do any type of conversions as well, or any types of mole ratios, you have to always start with a balanced equation. So let's go in and balance this equation so we can get started. So we have nitrogen on the left. We have 2 nitrogens, whereas we only have 1 on the right. We have 2 hydrogens on the left, and we have 3 on the right. So if we started with our nitrogens first, we can simply add a 2 here, which will give us 2 on the left and 2 on the right. That then gives us 6 hydrogens, so we can go into our hydrogens, and we add 3. So now we have 6 hydrogens on the left and 6 on the right. So now we have our balanced equation. So from here, we can now do several things. First thing we can do is we can do mole ratios. When doing a mole ratio, it's always important to look and see what is it asking you in the ratio. That's how you'll know what goes on top and what goes on the bottom. So suppose I wanted to know what is the ratio of nitrogen to the amount of hydrogens produced. The ratio here then would be 1 nitrogen to every 3 hydrogens reacted. And I said produced, that was my fault. So as I said, the question would be, what is the ratio of nitrogens to hydrogens? Or the question would say, how many moles of nitrogen reacts with the hydrogen moles? For every 1 mole of nitrogen that reacts, you have 3 moles of hydrogen. We're just going to type here that we're doing mole ratios. You can do several mole ratios. So there's another one. We could want to know, for every nitrogen that's produced, that reacts, how many ammonias are produced? So that would be 1 and 2 for every 2 NH3s. And put a space between here, it's a little jumbled up. We also may want to know, for every hydrogen that reacts with nitrogen, how many ammonias are produced? So that gives us, we have 3 hydrogens reacts, and that produces 2 ammonias. Or when we may want to know, for every nitrogen gas that participates in the reaction, how many ammonia are produced? So for 1 nitrogen gas, we produce 2 NH3s. And all of these can actually be done in the reverse. It may say, for every 2 nitrogens that we produce, for every 2 ammonias that we produce, how many nitrogens reacted? So in this case, you would do it in reverse. You would say 2 ammonias per 1 nitrogen. And as I said, you can use this ratio to calculate so many different problems, because what this tells you is what's the ratio. So then you can use this information to find out, well, if I have 5 moles of nitrogen, how many ammonias would I have? Let's look at an example using that. We have our ratios. So suppose the question says, and I'm just going to type it out, how many moles of nitrogen are needed to produce 5 moles of NH3? That's our question. How many moles of nitrogen are needed to produce 5 moles of ammonia? So in order to figure this out, we have to know the relationship of the nitrogen to ammonia, which we already know because we've done our mole ratios. Here's a key factor to knowing how to set these problems up. Always start with what's given. It's giving you 5 moles of NH3. Always write that first. Then, whatever you're trying to calculate, that should be the value that's on the top of the ratio. So I want to know how many moles of nitrogen do I need. So that's going to be the top part of my ratio. Now let's look at the relationship of nitrogen to ammonia in our reaction. So if we look at our relationship of nitrogen to ammonia, we see that we have 1 N2 per every 2 NH3s. So our equation then is going to be 5 moles of NH3, and I should have put moles in here, times 1 mole of nitrogen over 2 moles of ammonia. So then we would cancel out the moles of ammonia and this moles of ammonia. So if we work this problem out, 5 times 1 is 5, divided by 2 will give us 2.5 moles of N2 are needed to make 5 moles of NH3. That's what that problem was asking us. We can answer another problem with this same equation. Suppose it said, how many moles of hydrogen are needed to react with 3 moles of nitrogen? Once again, we're going to start with what's given. So we were given 3 moles of N2. I got that from the problem. Now, our top part of the ratio is going to be what we're solving for. So we want to know eventually how many moles of hydrogen do we need. So that's going to be our top part of our relationship when we look at the relationship between hydrogen and nitrogen. So from our equation, we already know that it's 3 moles of hydrogen for every 1 mole of N2. So our relationship is 3 to 1 for hydrogen to nitrogen. So now we simply calculate it out. 3 times 3 is 9. 9 divided by 1 is still 9. So we need 9 moles of H2 to react with 3 moles of nitrogen. I'll do one more from this equation. So how many moles of hydrogen are needed to produce 6 moles of NH3? Once again, we start with what's given. We're given 6 moles of NH3. We're going to multiply that by the ratio of hydrogen to ammonia. The relationship between hydrogen and ammonia is 3 to 2. So in our equation, for every 3 H2, we have 2 NH3s. That's our equation. So now we're going to do 6 times 3 is 18, and divided by 2 is 9. So in order to produce 6 moles of ammonia, we need 9 moles equation following the same rules. So I'm going to erase this. This is probably like it was when I was in class still learning how to do this board, but let's see if we can figure out how to erase it. Wrong eraser, that's the problem. Here we go. So let's erase all of this off. I'm sure it's a better way, but as I learn, it'll get better. Great, slowly but surely, got it. Let's look at a different equation. We're going to start off with our skeleton equation of aluminum. And I'm actually going to use the symbols just to kind of bring in information that you've learned before already. So plus O2, notice I put a 2 on there because oxygen is diatomic, gives us Al2 and O3. So that gives us Al2O3. Oxygen, I'm just going to go back and add that in there, which is a gas. And here we have a solid. All right, so we have our skeleton equation is aluminum plus oxygen gas forms aluminum oxide. So the first thing we want to do is balance our equation, of course. I'm just going to erase that off. So if we look here, we have 1 aluminum on the left, and we have 2 on the right. We have 2 oxygens on the left and 3 on the right. So let's look and see how we can possibly balance this particular equation. Now, of course, one of the simplest things would be to say, well, let's just put a 2 in front of aluminum. Now, if we put a 2 here, that doesn't actually balance our oxygens. We would still need to add something here. So by now, I'm sure a lot of you guys are very good at balancing equations, so you know to go ahead and just put a 2 here. That'll give us 4 aluminums and 6 oxygens. Then we can go on this side and add a 4. And then here, add a 3. So now we have all balanced. We have 4 aluminums on the left, 4 on the right, 6 oxygens on the left, and 6 on the right. So everyone's happy. So let's start with our mole ratios. We can do a lot of different types of mole ratios. So if we want to write them all out so we can just have them. And this is a step that if you're doing mole to mole or mole to mass or mass to mass conversions, unless I ask you specifically to write out the mole ratios, you don't have to just write them out. You can write them out for your own usage, but if you know how to simply look at the coefficients and know the mole ratios, then of course that's fine as well. So if we look to see the different mole ratios, we can look at the ratio of aluminum to aluminum oxide. So for every 4 aluminums, there are 2 aluminum oxides. You can also notice that there's a ratio between the oxygen and the aluminum oxide. So for every 3 O2, there are 2 Al2O3. What's the relationship between aluminum and aluminum and oxygen? For every 4 aluminums that it reacts with 3 O2. These are all moles, of course, and I'm just not typing in the abbreviation for mole. Or you may want to know, well, what's the relationship between the aluminum oxide back to aluminum? So how many aluminum oxides are produced per aluminum? So for every 2 aluminum oxides that are produced, you started with 4 aluminums. Or for every 2 aluminum oxides that were produced, 6 possible ratios you could come up with. Now let's look at some problems concerning it. So for problem 1, how many moles of aluminum are needed to form 3.7 moles of Al2O3? That's our problem. So first thing by now, hopefully you're remembering that you start off with your what's given. Now, what I recommend is you pausing this and attempting to work the problem yourself and then coming back and working through it with me to check your answer. So the first thing you want to do is start with what's given. You're given 3.7 moles of Al2O3. You're going to multiply it by the ratio of aluminum. You put aluminum on top because that's what you want to solve for. The ratio of aluminum to aluminum oxide. We've already determined that that was 4 to 2. So for every 4 moles of aluminum, you have 2 moles of Al2O3. So if we work this problem out, we can basically reduce this to 2, because 4 divided by 2 is 2. So 2 times 3.7 gives us 7.4. So what this problem says is 7.4 moles of aluminum are needed to form 3.7 moles of aluminum oxide. And that's basically because the relationship is 2 to 1. Look at another problem concerning this as well. Suppose you wanted to know how many moles of aluminum oxide will be produced when, when 5 moles of oxygen reacts with aluminum. So, first off, I'll give you a second to pause it. If you're working the problem. Now, welcome back. 5 moles of oxygen is what's given. I'm typing all kind of extra stuff, so sorry. Now we're going to look at the relationship of aluminum oxide to oxygen. Don't let that aluminum confuse you. I just threw that in there to let you know that's what's in the reaction. But we don't actually need to write anything about aluminum in our problem. So don't let that one throw you off. We're only concerned with how many moles of oxygen we start off with and the relationship of oxygen to aluminum oxide. So in our problem, we know for every 2 moles of Al2O3, we use up 3 moles of O2. So then we solve this problem. So then what you would do is 5 times 2 is 10, and 10 divided by 3 is 3.33. So what this is telling us now is that if we want to produce 3.33 moles of Al2O3, we can produce that from 5 moles of oxygen. And I'll do one more of just the simple mole-to-mole conversions. And we're going to say how many moles of oxygen are needed to react with 7 moles of aluminum. So our given is 7 moles. And what's our relationship of oxygen to aluminum? For every 3 oxygens, we have 4 aluminum. So we're going to do 3 moles of O2 and 4 moles of Al. And once again, we're simply going to do our calculation. So 7 times 3 is 21. 21 times divided by 4 is 5.25. So in answering our question, we need 5.25 moles of oxygen to react with 7 moles of aluminum to form aluminum oxide. And what I want you to know is in this problem, I could have put that in there. I could have said how many moles of oxygen are needed to react with 7 moles of aluminum to produce aluminum oxide. And I could spell. But I wouldn't want you to be thrown off by this because we're solving for how many moles of oxygen. So key thing to look at, the how many part, that's the part that's going to be on the top of your ratio. The given part, that's going to be who's on the bottom. All right, so hopefully that helps you understand mole-to-mole conversions and calculations. In a part 2 of this, I'm going to come back and give you examples of going from mole to mass.